In this video, I'll go through an example of Gram-Schmidt orthonormalization in R3. So we're going to start with this basis here. V1 is 0, 1, 1, V2 is 1, 1, 0, and V3 is 1, 0, 1. And we'll start by creating a set of orthogonal vectors by setting W1 equal V1. So W1 is just V1, 0, 1, 1. And then W2 will be V2, which is 1, 1, 0, minus the projection of V2 on W1. So V2 again 1, 1, 0, and W1 is 0, 1, 1. So if I figure out what that looks like, we're going to have, first of all, I'll just write down V2. And then I have to subtract the projection of V2 on W1. So first of all, let's take the inner product of V2 with W1, and that's going to give us 1. And then inner product of W1 with itself will give us 1 squared plus 1 squared, so 1 plus 1, or 2. And that's going to multiply the vector W1, which is 0, 1, 1. So that's going to give us, for the first coordinate, 1. Second coordinate will be 1 minus a half, so a half. And third coordinate will be 0 minus a half, so minus a half. Let's move on to W3. So first of all, let's write down V3. 1, 0, 1, and then we're going to subtract the projection of V3 on W1, where V3 is 1, 0, 1. So inner product of V3 with W1, so V3 is 1, 0, 1, W1 is 0, 1, 1, so that will have inner product 1, and then the inner product of W1 with itself, we figured that out before, that was 2. Okay. And then, oops, getting ahead of myself, we need to subtract projection of V3 on W2. So inner product of V3 with W2. So V3, remember, is 1, 0, 1. W2 was 1, a half, minus a half. So we're going to have 1 and V3 with W2. So we're going to have 1 minus a half, which is a half. And then in the denominator, we'll have inner product of W2 with itself. So W2 is 1, a half, minus a half. So we'll have 1 squared plus a half squared plus another half squared. So we'll have 1 plus a quarter, so 1 and a half. Let's write that down as 3 over 2. And we are multiplying that by W2, which is 1 half minus a half. Okay, so putting all that together, let's see what we have. I'm just going to do this in 2 steps. So we'll have 0, 1 half, 1 half, and then here, so 1 half divided by 3 halves is going to be 1/3. So we'll have 1/3, and then a third times a half, 1/6, and then a third times minus a half, so minus a 1/6. Okay, so in the first coordinate we have 1 minus 0 minus a third, so we'll have 2/3. Second coordinate, 0 minus a half minus a sixth, so that's going to be minus 2/3. And then third coordinate, 1 minus a half plus a sixth, so that's going to be plus 2/3. Okay, so we can do a quick check here to make sure we've got orthogonal vectors. So W1 is 0, 1, 1. That's orthogonal to W2, which is 1, a half minus a half. And it's also orthogonal to W3, 2/3 minus 2/3, 2/3. And then W2 and W3 are also orthogonal if we look at them, because they're going to have inner product 0. 1 times 2/3 plus a half times minus 2/3 plus minus a half times 2/3. That will be 0, inner product of 0. Okay, let's orthonormalize these basis vectors now. So that means to make them have length 1. So we need to figure out the lengths of these vectors and then divide by that length. So we're going to normalize the vectors. So the first one, W1, that has length, so it's 0, 1, 1. So the length of that is going to be the square root of 1 squared plus 1 squared, so the square root of 2. And then the length of W2, so W2 is 1 and a half and minus a half. So we're going to have the square root of, let's see, 1 squared, so 1 plus a half squared, quarter plus minus a half squared, so another quarter. So we'll have square root of 3/2. And then finally W3, we've got the square root of, what have we got? We've got 2/3 minus 2/3 and another 2/3. So we're going to have 3 times 4/9. So let's simplify that. So that's going to be square root of 4/3. I could simplify this by pulling out the 4, as that has square root 2, but I'm going to just leave it as it is for now, because that's going to make the calculations that we have to do in a minute simpler. So I've got my lengths, and so now I just need to do the last step, which is to normalize the vectors W1, W2, and W3 to get U1, U2, and U3. So let's do that. So U1 is going to be 1 over root 2 times 0, 1, 1. So it's good practice to have square roots in the numerator rather than the denominator. So if I multiply through by root 2 over root 2, we'll have root 2 in the numerator and root 2 times root 2 in the denominator, which comes to 2, so we'll have root 2 over 2. So I'm going to write this vector as 0, root 2 over 2, and root 2 over 2. It's our first vector. Then the second one is going to be 1 over the length of W2, and the length of W2 is square root of 3 over 2. So if I flip that up the other way, we'll have square root 2 over 3, and then that's multiplying the vector 1, 1/2 minus 1/2. So if I simplify that, we're going to have, let's see, we could write this in a few different ways. Root 2 over 3, and then 1/2 of root 2 over 3, and then minus 1/2 of root 2 over 3. But I don't really like having the square root 3 in the denominators here, so going to do is I'm going to multiply numerator and denominator by root 3 to get rid of that root 3 in the denominator. So that means I'm going to end up with root 6 over 3, and then root 6 over 6, and then finally minus root 6 over 6. Finally, W3 is going to be 1 over the length of W3. So length of W3 is root 4 thirds, so root 3 fourths, and that's going to multiply the vector 2 thirds minus 2 thirds and 2 thirds. And again, let's simplify that. So we'll have 2 thirds of root 3 over 4 and minus 2 thirds root 3 over 4 and 2 thirds root 3 over 4. And again, I don't really like having square roots in the denominator here, so if well, those will cancel with so root 4 in the denominator will cancel with the 2 in the numerator, so that's going to end up being root 3 over 3 and minus root 3 over 3 and root 3 over 3. And then we have our orthonormal basis starting from this basis here, and we've applied the Gram-Schmidt orthonormalization process and ended up with these three vectors, u1 and u2 and u3.